Today is November the 6th, 2022. And since I'm on kind of a roll tonight, something I've been thinking about, got plenty of time nowadays, is I see some videos out there on how to determine the gain, it's also known as mu, of a tube. The gain of a tube, let me turn this over so I can write it on a little bit, but it won't go all the way through. The gain of a tube, you can call it gain, which is also the same thing as mu, which is also symbolized by the Greek letter mu. These are all the same thing. They all mean the same thing. And the way that you determine it is by determining the delta, that's the change in voltage of the plate, divided by the change in the voltage of the grid. And it equals some number. And it's called a dimensionless number because when you're dividing a dimension of voltage by a dimension of voltage, and when you divide a dimension by the same dimension, you get one. Not one dimension, you just get one. It's a dimensionless number. Like if you divide cats by cats, 3 cats divided by 1 cat is 3. But it's not 3 cats, it's just 3. It's a dimensionless number. I don't want to overdo that. But anyway, and the way that you get this number is by holding the plate current steady. So you, that's what this right here is for. Look at that, I wrote on it a little bit, but that's not too bad. Okay. First of all, you probably want to look at the tube and find out where it's supposed to normally operate, because these curves operate, you know, these curves are drawn way out of the normal operating range of a tube. But let's say you're going to operate the tube Class A. This is a 300B. Beautiful tube. I love the 300B. And you know what's amazing about it is these things put out, look at the plate dissipation, not put out, but look at the plate dissipation of a 300B. It's 36 watts. Man, that thing can get hot. Of course, it's a pretty big tube. But let's look at the typical operating conditions, and we'll see that it's typical. Let's see, what's its plate current? We want to know its plate current. Grid voltage, 0 signal plate current. There we go. 62 milliamps. Its maximum signal plate current, 74. So we want something in that range right there. I'm going to circle that. See, we want something in its normal operating range. That's a good place to start, okay? And we're going to hold this number constant. So what we do is we look here on the graph that has plate. I got to move my camera just a little bit. I keep wanting to get too close here. It's got to have plate current on one side because this is a constant. We're just going to draw a straight line across from some level, and we determine between like 60 and 72. So 60 and 72. I don't know. Let's choose 70. See right here. Plate current in milliamperes. We're going to choose 70 because that's about in the middle. Doesn't have to be in the middle, but you know, you want it to be. We're going to draw a line straight here. I'm going to use red for this. Hope I don't make a big mess on my ruler. Let's use this one. 70. I'm making it red so we can, because we're going to draw some more lines on it too. This is what we have to hold constant. Okay, that's it right there. Now we remember we want to know the ratio of the change in plate voltage. This is the plate voltage. This is the plate current, and this is the grid voltage or bias. It's the grid voltage. And we want to know what the change in grid voltage is, and then we want to know what the change in plate voltage is. Well, we'll just pick some easy points here. Let's just pick these 2 points right here. Here's 200 volts, and here's 250 volts. So we already know what our delta VP is, because we chose it. It's 200 to 250, so it's 50 volts. It's that difference there. Now, the rest of it is actually pretty simple. We have to take the 200 and where it intersects this line, and we draw a straight line down. You can see this. And we're going to have to read that voltage right there. And then at 250, we do the same thing, draw a straight line down. They're not exactly on boundaries, so we got to interpolate just a little bit. Well, let's see, here's minus 20, 25, 30, 35. So it's a little bit less than 35. Let's call it 33. And this one is 40, 45, 50, 55, 60. Yeah, you got to make sure you got your graduations in there correctly. Let's see, minus 40, minus 45. We'll call this like minus 47. These are both negative, not that that really makes any difference in the calculation. So we subtract 33 from 47. 47, enter, 33 minus, and we get 14. So this equals delta voltage grid, which equals 14. So we've got our two numbers here, 50 and 14. And the gain is just simply this number, the change in plate voltage that we selected over the change in grid voltage, which we determined by our straight lines. So 50 divided by 14 is 3.57. That's our number. That's what we say it is as best we can read it. 3.57. And it's going to change slightly as because these curves are not perfectly straight. And then we look back. Now that we know how to do this, we know we've got it figured out. This is our magic number right here, 3.57. This is the gain, like I say, also known as mu, written out like that, or the symbol mu, 3.57. And they say that it is 3.9. That's close enough. That's the number. That's how you do it. There goes a helicopter over it. It doesn't need to be any more complicated than that. Now there are some other relationships that if you go look at a tube data sheet, you'll see. And there's three things that are pretty important in vacuum tubes, especially triodes. Let's just go to triodes right now. One of them is the gain, which we just determined. Another one is RP. That's the plate resistance. There is a value in here called plate resistance. Let's see if we can find it. They call it plate resistance. Let's do this. Plate resistance. This is not load resistance. This is not the resistance that you want to put as an output transformer. See, it's 740. See, plate resistance, 740, and it's usually listed as a little r and a p, resistance of the plate. So it is, what is it, 740. Let's see, where am I writing now? 740. RP equals 740. And the other thing we want to know is GM. That's its transconductance. Also now known now, because they changed the name, because transconductance is measured in mhos, which is ohms spelt backwards. Ohms. And the reciprocal of ohms, 1 over ohms, equals mhos. Or it's also known as Siemens. Yes, I don't know if I spelled that right. I'm sorry. I'm not trying to make a joke out of this. But anyway, that's what they do. So let's don't sweat over that. All of the old books will tell you it's in mhos. Okay, now how do you remember the relationship between this? It's really pretty simple. GM is always going to be a small number. It's going to be measured in the micro or the milli range. Micromos, millimos. So that means it's going to be GM. I don't keep this in my head. I just remember how to do it because I know it's going to be a number much smaller than 1. It's going to be a number up here. It's going to be a small number divided by a large number, or a relatively large number. So GM, in our case, equals a small number, which we'll use their number. What did they say it was? 3.9? 3.9. This is its GM, which is equal to mu over RP. Let me write that again. GM equals mu over RP. So it's 3.9 over 740. 740. This is a real number. 3.9 divided by 740, not 750. 740. 740. I just don't want to do these videos over and over again, so 3.9 740 divide, says it's 0.01, but we have to expand this here, F fix 9. So it's GM equals 0.005270270. We'll just write the whole thing out. Now, if you want it in micro, you just move the decimal place over 6, because micro is the same as a 1 millionth, right? So we move it over 1, 2, 3, 4, 5, 6, right there. And we say it's 5,270 micromos. That's a real number. Let's see what they say it is. I think they give GM in here. If they don't, that's still a real number. GM. Now, they may not have it for a triode. Plate voltage. Yeah, they do too. Look, they got 5,300. I'm sorry, I drew a line through it. 5,300. But for different current values, it's going to be slightly different. But it's still in that same range. They got 5,300, and we got 5,270. There you go. That's what you need to know about tubes as you're selecting them. Now, of course, once you select them, now you've got to know its plate voltage. You've got to know its filament voltage and filament current. You've got to know its maximum plate dissipation, so you can set its bias and set its resting plate current, etc. And you know, there's all those details. And then you want to know its plate load resistance. I'm going to go one step further here that may not be common knowledge, and you will actually see this listed in some of the older tubes, and this may surprise some of you. In today's world, when we look at a push-pull amplifier, we got the plate here, and it goes down here to this plate, right? And then the center tap goes off to the B+. Well, a reasonable value for this right here, for like say 6L6s, for example, I like to use 6L6, it's so common. The plate load resistance from plate to plate is generally listed as about 5K. It's a real common value. You see that in just about all the tube manuals. We will see it in all the tube manuals. Okay, it's 5K, but since this is an inductor, its impedance and its inductance values are the square. So what that means is, if it's 5K from here to here, it's 1.25K across here, and it's 1.25K across here. I didn't draw that very well. Let's draw it again. Let's just draw the transformer without the tubes. And this is the center tap. If it's 5K from here to here, it's 1/4 of that across each one. So it's 1.25K from here to here, and 1.25K from here to here. This is true. Okay, and here's going to be the part that might surprise you. Well, one more thing about it. If its inductance is 20 henries across the whole thing, it's 5 henries across half of it. Just like the impedance. And the reason that is true is because if you take a coil and it's got an iron core, say, we're going to draw this, and you wind a whole jillion bunch of turns and you bring a wire out here, and let's say this is 5 henries. And then you wind exactly the same number of turns again, and another whole bunch of turns, and you pull it out here, and then this is 5 henries. You know, from one side to the other to the center tap, and this one to the other. Since these are wound on top of each other, if you look up the formulas for it, you'll see that it's actually 4 times that, or it'll be double. It'll be 4 times 1 winding because they're wound on top of each other. Now, if they were wound, if they were wound like this, well, if they wound on the same core, I'm not exactly sure what would happen on the same core, but not on top of each other. I'm not exactly sure what that one would be, so I better not talk about it. And it's the same thing for the impedance. Okay, now you know where this is going? Where this is going is that in your amplifier, back to the tubes, here's your plate of one tube, here's your plate of the other tube, and your push-pull amplifier. So if you're overly obsessed with the inductance of your this goes to the power supply. If you're over the concerned with the inductance of your transformer, and you got a 20 Henry here, but you only got 5 here, and you only got 5 here. This point right here is at signal ground, and I don't mean like it's at AC signal ground, not AC like the AC input current, not like 60 and 50 hertz, not power supply, but the signal voltage, what's driving the grids of these tubes. This is at signal ground because what's the first thing that you're going to encounter when you get to the power supply? You're going to encounter that big electrolytic capacitor. So all of the audio that this tube is developing across this transformer is developed across here to here, from one side to the center tap, and then the other half is this tube from this side to the center tap. I apologize for my mess here, but I am not an artist, obviously. So your 20 Henrys or 40 Henrys or whatever, I've been there. I've been obsessed over this until I actually had to figure it out. But my tube is operating across 5 Henrys, and people get really obsessed about this and think you need 40 and 50 and 100 Henrys like in an SET amplifier. Well, think about it, and you may realize that you just may not be taking everything into account. So we've got the gain, we've got the transconductance. We know these values. These values are going to be in every decent sheet. You don't have to figure them out, but sometimes you do. Sometimes they don't tell you what you need to know. Seems like there was one other detail of this that I don't remember right now. We got the gain, we got the deltas, we've got the chokes and the Henrys and all that kind of stuff. Yeah, now again, I'll go back to this one. Since these are wound on top of each other, oh, I know what I was going to tell you. If you take a big output transformer, and this is the primary winding with a bajillion turns on it up here, and you measure its DC resistance. I gotta do this again. I can do better than that. If you do the DC resistance of it, there you go. Now that's a real transformer, isn't it? And here's its center tap. If you take a very accurate ohm meter and you measure DC from here, DCR from here to here, and you measure DCR from here to here, they're going to be slightly different. And the reason being is one winding, the outer winding, has a larger diameter to go through as it's wound. And the important thing is not the DCR. The important thing is that there be the same number of turns in this half as there are on this half. Because each turn cuts through the magnetic flux, and each turn matters. So if you got 4,000 turns here, you got 4,000 turns here. But this one, assuming this is the outer winding, they're all wound on top of each other, remember? This one's got more length of wire in it because the diameter is bigger. You know, the more wire you wind on it, the bigger the diameter gets. And if you measure the inductance, it might actually measure ever so slightly different. But don't forget that part right here, that this and this, from here to here, and here to here, is 1/4 from here to here. So keep that in mind next time if you are stressing over how many henries you need in your output transformer, and especially SET stuff that people get really obsessed about. And common value for a good UTC transformer or Acrosound is about 20 henries from here to here, 5 henries across each one. Hope this helps. Thanks for watching.